Okay, this is Math 2. We're going to do 26, 27, 28, and number 31 from Chapter 8. See, on the first one we have examine the geometric relationship in the diagram at the right, show all the steps in the solution for x and y, and then, what does it say? Named a polygon. Okay, so, let's see, we have 1, 2, 3, 4, 5, so it's obviously a pentagon of some sort, and then, I guess since every angle is pretty much the same, that would make it a regular polygon, which makes us very happy because now we can do what we know how to do. So what you do, so you have 5 sides, right? So you're going to take 5 minus 2, and then we're going to multiply it by 180, so that gives us 3 times 180, which gives us what, 540? I'm assuming. I can't remember. You never remember 3 times 180 in my head. Yep, 540. Okay, so that means every single angle in here, and I'm going to do this in red right now. So every single angle, so this red angle, or fuchsia or pink or whatever you want to call it. So all of these 1, 2, 3, 4, 5 angles all put together should come out to 540. But I want just the y part of it, right? So now we're going to do divide by 5. So we're going to take 540 and divide by 5. And we're going to get 108. So every single pink angle is going to be 108 individually, right? So this is 108, this is 108, this is 108, this is 108, this is 108. And then technically the y is going to be half of that because the radius of any polygon, and this is the radius of a polygon, goes from the center to the vertex, is going to cut that angle in half. So half of 108 is, oopsie, is going to be 54. So 108 divided by 2 is going to be equal to 54. So y is equal to 54 degrees. Alrighty. So now we know this is going to be, I should do this in a different color so you're not confused. Y is 54. So this is 54 degrees, this is 54 degrees, this is 54 degrees, that's 54 degrees. You get the picture. Okay? So if that's 54 and that's 54, technically over here you have a triangle, right? It looks like this. This would make it 54. This would make it 54. And the question is, what is x up here? Because that's still a triangle. Okay, so you can find x on your own there. 27. Joey uses 10 congruent isosceles triangles to create a regular decagon. What are the 3 angle measures of one of the triangles? Explain how you know. If the area of each triangle is 14.5, was the area of the regular decagon? Oh, okay, that's cool. So let's see. So decagon, so that means it has 10 sides. So we have, where's the black one? What happened to the black? Oh, there it is. So we have 10 sides minus 2 times 180. So that makes it 8 times 180. So 8 times 180 is 1440. Okay, so all of the angles inside, right, add up to 1440, but I only want, I don't know, let's say one of the pink ones, right? So I'm going to take 1440 and divide by 10. That gives me, well, should give me 144. I don't know why I did it on the calculator, but it's too early in the day, I guess. Okay, so one of the pink ones is 1440. I'm sorry, 144. Okay, so this is 144, but I want half of it. So, let's see, divided by 2 is going to give me 72. All right, so 14 divided by 2, 72. So that means this angle here is 72. This angle here is 72. Sorry if you can't see. So they're all like 72, 72, 72, 72, 72, 72, all the way around, right? So here's one of the little triangles in there. and this would make it 72. This would make it 72. And the question is, what is the last one? That's what it wants to know. So it's basically, it's basically doing the same thing that you did for number 26. Okay, now, it says each of the triangles 14.5 square inches. What is the area of the regular decagon? So each triangle has an area of 14.5. So this is an area of 14.5. This is an area of 14.5. And essentially you have like 1, 2, 3, 4, 5, 10 of them, right? Okay. Well, if the whole area of one of them is 14.5, and you technically have 10 of them, then 10 times 14.5 should give you 100, what is it, 145 inches squared. So that's the area of the whole polygon, or in this case, decagon, because that's what it is. Okay. All right. That's 26 and 27. 28. Let's see. We have Ben is designing a logo for the Math Club t-shirts. He has sketched a possible design on tracing paper shown as the right. Explain how he can locate the center of the inscribed circle. What is that point called in relation to the circle? Okay, so basically what we want to find is, this is the, not the circumcenter, this is the, oh my goodness, I'm drawing a blank right now. Where's 8.1.1? Because the math notes there were really good. The incenter, yeah, this is the incenter. Okay, so in order to find the incenter when the circle's on the inside, what you need to do is you need to cut every single one of these angles in half. You want the angle bisectors. So unfortunately I'm going to have to eyeball this because I don't have my protractor anywhere near me, and this video has to go on. So I kind of eyeball this, and I need a pencil. I can't do this with a pen, just in case I mess up. This should work. Okay, so this looks about like the middle. This looks about right. It's probably not right, but that's okay. Right now, it's the best I can do. That should be, so then this angle here is the same as that angle there. And then we're going to do the same thing for this one. Explain how he can locate the center of the inscribed circle. Oh, angle. So angle bisectors. You're basically just doing angle bisectors in all of these. And it should give you the center of the incircle. Yep, okay, there we go. Okay, so there we go. Angle bisectors, create, what are we doing? Create 3 angle bisectors. Okay, their point of intersection is the center of the incircle. What is that point called in relation to the triangle? Isn't it the centroid? I'm pretty sure it's the centroid. I forgot. This is not a good... no, not really. Let's just call it incenter. From the inscribed. Their point of intersection is the center of the circle. Let's just say circle. And then what is the point called in relation to the triangle? The point is called the incircle. There you go. Alright, that's better. Okay, and the last one is calculate the area of an equilateral triangle with a side length of 20 millimeters. Draw a diagram, show all your work. Okay, so equilateral triangle. I'm just going to pretend this is an equilateral triangle. These are all 60, 60, 60, right? All right, and the side length is 20, so that means this is 20, that means that's 20, and the bottom's 20. They're all 20 a piece. Now, you want the area, right? So you eventually have to find the height of the triangle, which is this one right over here. So, technically that's your altitude, because it's a 60, 60, 60. We're dropping it down from a vertex. We'll make a 90-degree angle with the opposite side. So these two halves should be the same, technically, because this is an equilateral triangle. So now, that makes this part 10 and this part 10, which is wonderful for us, because now we can actually calculate the height, right? So we have, let's call it x, because I have nothing else to use right now. So x squared plus 10 squared is 20 squared. So x squared plus 100 equals 400. So x squared equals, what is this, 300. So that would make x equal to 10 root 3, which is pretty much the same as, I don't know, whatever 10 root 3 is. Ooh, battery's low. That's not good. Off. I thought I turned that off. 10 times 3 squared. Well, whatever that is. Where's my square button? Okay. 17 point something. 32? Somewhere around there. Okay, so now you just need to calculate the area of the triangle. So area of the triangle is base times your height divided by 2. Your base is 20. Your height is 17.32-ish divided by 2. And then you can find the area of that triangle. All right, that should be it. If you have any questions, please see me. If not, I'll see you later in class.